This is the second part of chapter 0.7, probability. I'm going to start with some sample space though, just to get started. Find the sample space for each of the following. One coin is tossed. Okay, the sample space just simply means what are the possible results. So the sample space will be the set. If you toss one coin, you're either going to get heads or you're going to get tails. That's our sample space. Heads or tails. What if two coins are tossed? Well, the first one could be heads and the second one heads. First one heads, second one tails. That's all with the first one being heads. First one could be tails followed by heads. Or it could be tails and tails. So that is our sample space. So there are four possible things that could happen if the two coins are tossed. Now what if three coins are tossed? Start with the first one being heads. Well, second one could be heads. Third one could be heads. First two heads, last one tails. So that's all the possibilities with the first two both being heads. Now, what if the first is heads and the second one's tails? Well, what about the third one? Well, it could be a head or it could be a tail. And that is all the possibilities with the first one being a head. Now let's repeat the same process with the first one being a tail. We could have tails followed by heads. Now what are the possibilities here? For the third one, could be a head, could be a tail. That's all the possibilities, tails, heads. Now tails, tails. Third one could be a head, third one could be a tail. We've exhausted all of our possibilities, and we are left with a total of 8 things. 8 possible things in our sample space. All right, now, why is that important? Because the sample space is your total number of possible outcomes, which is important when it comes to probability. The probability that an event will happen equals the number of outcomes in the event. Usually I simply say the number of ways of getting what it is you want, whatever it is we're trying to do, divided by the total, which is the number of outcomes in the sample space. So I usually kind of think of this as want over total, but it's the whatever the event is you're trying to get divided by the sample space, number of outcomes in that sample space. So question number 2 here. 2 coins are tossed. What is the probability that both land heads up? So the probability of this event. So how many are there when 2 coins are tossed? Here's what we're looking at. So how many are there where they're both heads? I'll switch colors here. There is one where they're both heads. So there's only one way of getting what we want out of a total of how many possible things? 4. So the probability of this event, probability of both being heads, is 1 out of 4. And that's basically what we're doing. We're going to expand on it as we go through this though. Number 3, a card is drawn from a standard deck of playing cards. What is the probability that it is an ace? Okay, it is assumed that you play with standard decks of cards and you are familiar with certain things. For starters, what is the probability that it's an ace? So the probability of the event, the probability of an ace, it is assumed that you know that there is an ace of spades, ace of hearts, ace of clubs, and ace of diamonds. There are 4 aces. So there are 4 ways of getting what we want in a standard deck of playing cards. has a total of 52 cards in it. That's basically our answer, but that reduces. And again, reducing that's easy if you do actually play cards and you know that there are 4 suits and there are 13 cards in each suit. So you would know 4 times 13 is 52. Just normal arithmetic, you may not know that, but if you play cards, you would. So anyway, back to this problem. What's the probability that's an ace? There's a 1 out of 13 chance of drawing an ace. Page 2. 2 6-sided dice are tossed. What is the probability that the total of the 2 dice is 7? Well, 2 dice are tossed. Again, it's assumed that you know that each die has numbers 1 through 6 on it. So to get a 7, we could have a 1 and a 6, a 2, 5, 3, 4. That is not a 4. Try that again. 4, 3, 5, 2, and a 6, 1. So how many different ways are there to get what we want? 6. So the probability of this 7, there are 6 ways of getting what we want. How many total things do we have in our sample space? How many total possibilities are there? Well, there's 2 6-sided dice. Then our sample space will be 36 elements. So probability of getting a 7 would be 6 out of 36, which reduces to be 1 out of 6. All right, next. In the Arizona State Lottery, a player chooses 6 different numbers from 1 to 41. If these 6 numbers match the 6 numbers drawn in any order by the Lottery Commission, the player wins the top prize. What is the probability of winning the top prize if the player buys 1 ticket? So we're going to buy 1 ticket. So make that an equal sign instead of a dash. All right. So how many ways are there to get what we want? There's only the 1 winning ticket. How many possible lottery tickets are there? Well, you're choosing 6 numbers from 1 to 41 in any order. So the number of our sample space in any order. Order does not matter. Makes it a combination. From 1 to 41 means there are 41 numbers, and we are choosing 6 of them. Now, what is that? Let's see, calculator, menu, calculator, menu. This is under probability. You go under probability, they have factorials, permutations, combinations. We are doing a combination. Now, you have to know how to enter in the calculator. If you're using a calculator, they want 41, comma, 6 for this calculator. You have a different calculator at home. You're going to have to enter it differently. So you have to know your calculator. Some calculators, you have to hit the 41 before you go choose the combination formula and then the 6 afterwards. So you actually have to type it in the way we write it. All right, but in this case, 44, what is that? 4,496,388. $4,496,388. So, what is the probability at this event we have the winning ticket? What's the probability that that happens? 1 out of 4,496,388. Alrighty. Next, probability of the union of two events. Okay, first, now make sure we understand this notation. That thing there that kind of looks like a U, it is not a U. Little horseshoe looking thing, but it looks like a U, stands for union. Okay, your union statements were your OR statements, if you remember that from earlier this year as well as Algebra 2. If it's turned the other way around, that is your intersection symbol. Okay, so the AND statement, if you were to draw a line here, right there, kind of looks like an A. We're not going to draw a line there, but there's like an A for the AND. But your union and your intersection. Okay. Probability of the union of two events. If A and B are events in the same sample space, the probability of A or B occurring is, or tells us we're doing union. So the probability of A or B will equal the probability of A plus the probability of B. So we're adding here probability of the first plus the probability of the second. But you must subtract their intersection. All right, now I'm going to skip this next part. Let's just go ahead and jump down to number 6. One card is selected from a standard deck of 52 playing cards. What is the probability that the card is either a heart or a face card? Again, there's lots of assumptions here that you actually are familiar with the deck of cards. So we're looking for the probability of a heart or a face card. So I would say probability of heart union face card. That's what we're looking for. According to our formula up there, it would mean the probability that we get a heart plus the probability that we get a face card, but you have to subtract the probability of heart intersect with face card, which means that's a heart and a face card. Or in other words, your face card hearts. Well, how many hearts are there in a standard deck of cards? 13 out of a standard deck of 52 cards. Plus, how many face cards? Your face cards are the cards that have pictures of faces on them, which would be your jack, queen, and king. So you got a jack, a queen, and a king. So you've got 3 face cards per suit or 4 suits. So that's 12 out of the 52. Minus, how many are heart and face cards? So how many? So in other words, I want the jack of hearts, the queen of hearts, and the king of hearts. So 3 out of the 52. Now this is the key to the problem. Why are we subtracting that? Well, the reason is real simple. That jack of hearts, queen of hearts, and king of hearts We counted them right there when we counted our hearts, but we counted them again right there when we counted the face cards. So we counted them twice. So, and we don't want to count it twice. So to fix that, where we counted them a second time, we have to subtract it out. So that's the reason for that. And now just do the math. So 13 plus 12 minus 3 gives us 22 out of the 52, which does further reduce. Now, back to this other thing. So I'm now coming back to this part right here. If A and B are mutually exclusive, then the probability of A or B is simply the probability of A plus the probability of B. Now that part right there is kind of, it's really redundant because mutually exclusive means there's no chance of any overlap. Well, if there's no overlap, then the probability of A intersect B would simply be subtracting 0. And if you, so really this formula is just an extension of that formula in the first place. So really all you need to know is that formula, and it really applies in all cases. Just know that if they are mutually exclusive, you're not going to get an intersection in the first place. So you don't have to worry about it. That's all that part is saying. All right, flip the page, page 3. The personnel department of a company has compiled data on the number of employees who have been with the company for various periods of time. The results are shown in the table. If an employer is chosen at random, what is the if an employee is chosen at random, what is the probability that the employee has, question A, 4 or fewer years of service, and question B, 9 or fewer years of service? So there are 157 employees with 0 to 4 years of service. 89 have 5 to 9 years of service, so on and so forth. So for part A here, the probability of 4 or fewer simply means the probability that they have 0 to 4 years of service. Well, that's easy enough on knowing how many that would be. Just read it right off the chart. 157 over. How many total? Well, we got to take that part right there and add them up. So when you add them up, I'm cheating, looking on my paper, it added up to be 529. So that is our answer to that part. Now, part B, same general question, but now I want 9 or fewer. So the probability of 9 or fewer. Now, some of you would jump ahead and get the answer pretty quick, and you'll be correct, but bear with me on how I'm doing this. I'm trying to demonstrate the point that the book wants to demonstrate. The 9 or fewer would be these two categories, agreed? Which means the first category, 0 to 4, union with the second category, which is 5 to 9. Is there any chance of overlap? And the answer is no. You've either got, your number of years of service is definite there. So these two are mutually exclusive. So the point of that is it's simply going to be the probability of the 0 to 4 group plus the probability of the 5 to 9 group, and we don't have to worry about their intersection. So the 0 to 4 group would be 157 over the 529. The 5 to 9 group is 89 over 529, and we simply add those up. But that was their attempt at showing us an example with mutually exclusive. All right, next thing. Two events are independent if the occurrence of one has no effect on the occurrence of the other. Okay, it's kind of like if you're going to flip a coin 3 times. Does the fact that the coin came up heads the first 2 times have any bearing on whether it's going to be heads or tails on the third flip? And the answer should be no. It has no bearing on it whatsoever. All right, so what is the probability of independent events? If A and B are independent events, the probability that both A and B will occur. So there are 2 independent events, but I want A and I want B to happen. You simply do the probability of A, you do the probability of B, and you multiply. So looking at our example here, number 8. A random number generator on a computer selects 3 integers from 1 to 20. What is the probability that all 3 numbers are less than or equal to 5? So the probability of our event that we're after here is going to select 3 integers. Okay, for the first integer, what is the probability that it is less than or equal to 5? Well, that means it could be a 1, a 2, a 3, a 4, or 5. So there are 5 ways of getting what we want out of 20 possible things, 20 possible integers. Now, what about the second integer? What's the probability that it is less than or equal to 5? Well, the first one's got no bearing on it. It's independent. It's still going to be 5 out of 20 as well. What about the third integer? Still 5 out of 20. And we always multiply. Now, in this case, I would actually reduce first. It'll make the multiplication so much easier. But there's only a 1 out of 64 chance that all 3 of them are 5 or less. All right. Now, page 4. Yeah, page 4 gets a little trickier. All right. In 2004, approximately 20% of the adult population of the United States got their news from the internet every day. In a survey, 10 people were chosen at random from the adult population. What is the probability that all 10 got their news from the internet every day? So the probability of our event, and calling it A just at random, probability of the event, they surveyed 10 people. What's the probability that the first one got their news from the internet? 20%. That's 20 out of 100. So that is a probability. Now, what about the second person? 20%. What about the third person? 20%. Fourth person. Fifth person. Sixth person. Seventh person. Eighth person. Ninth person. And the 10th person. Bottom line, 20% is 0.20 to the 10th power. Because I don't want to do that if they're, what if they surveyed 1,000 people? I definitely don't want to be writing 20% 1,000 times. It's just simply 0.20, 20%, for the 10 people to the 10th power. So let's see, 1, 2, 3, 4, 5, 6. Well, that should have been obvious. 1, 2, 3, 4, 5, 6. 1, 0, 2, 4. Again, just writing the answers that I already have here. Okay. Now, shifting gears slightly. The complement of an event A is the collection of all outcomes in the sample space that are not in A. The probability of a complement. let A be an event and let A prime be its complement. So if the probability of A is probability of A, the probability of the complement will be 1 minus the probability of A. In other words, if there is a 20% chance it's going to rain today, what's the probability that it's not going to rain? 80%. How did you get 80%? You did 100% minus 20. 100% is just another way of saying 1. If there is a 5 out of 7 chance you're going to win, what's the probability that you lose? 2 out of 7. How'd you get it? 1 minus the 5 out of 7. So the formula here is simply 1 minus whatever it is we're after to get its complement. Now that leads us to this last example, though, a little more complicated than the two I just used as quick, easy examples. A manufacturer has determined that a machine averages 1 faulty unit for every 1,000 it produces. What is the probability that an order of 200 units will have 1 or more faulty units? Now, the hard part about this problem is not just that it's 1, but 1 or more. So in other words, what's the probability that it has 1 faulty unit? What's the probability that there are 2 faulty units? 3, 20, 100. Okay, that makes it really tricky, really difficult in itself. So let's go the other direction. What is the opposite of 1 or more? That would be none are faulty. Now that is just one simple case. That is so much easier to work with. So let's work with that. What's the probability that none are faulty? We're going to call that our original event A. Probability that none are faulty. Well, what's the probability that the first one is not faulty? Because we're saying none, not faulty. Well, if 1 is faulty out of every 1,000, that means not faulty would be 999 out of 1,000. Agreed? Now, what about the second unit? It's going to be the same thing. What about the third unit? Same thing. How many units are we looking at? 200. So we're going to raise this to the power of 200, which is the exact same thing we did up here with this problem on number 9. Same concept. Now punch that out in your calculator. And I'm sure it kept going, but we rounded to 3 decimal places on my paper. So the probability that none of them are faulty is 0.819. That's not what we're looking for, though. We want the probability that 1 or more are faulty. Well, that would be the complement of our event A, which is simply 1 minus the 0.819, which gets us 0.181. Turned out to not be such a difficult problem after all. And that was chapter 0.7, the second one, our lesson in probability.